that we learned in PRC1 that there is a composite action, steel and concrete are bonded together. There is a perfect bond between steel and concrete, and there were few assumptions on the cross section, plane section remain plane. There is a perfect bond between steel and concrete, and on our cross sections we considered that T is equal to C. So tension is equal to compression. Now the tension, we have idea that tension is developed by steel because concrete is weak in tension, while compression we can develop through concrete. But we have the idea that C is equal to T, and this equilibrium equation is valid when there is a perfect bond between steel and concrete. C we can develop from concrete, plus we can also develop compression force through steel. But you know very well that tension we can only develop from steel because concrete is weak in tension. So tension of steel is reasonably high, and if I have some tension from concrete, that is so negligible that we do not consider it in our equation. Once modulus of rupture will approach, steel strength, concrete strength drop to zero. But this T I can only get if there is a perfect bond between steel and concrete. If there is no composite action, then this equilibrium can't be established. So we know it very well. Now I will try to explain that through which mechanism this bond is developed between steel and concrete. And moreover, I will try to explain that which length I need, how much length is important to develop the steel, and development means or develop means that length which is required to let the steel yield, because I can't get yielding of steel in the reinforced concrete until and unless it is perfectly gripped. So without gripping it, without holding it in the concrete mass firmly without slip, I can't get neither composite action nor this equilibrium equation will be valid. I can give you very simple explanation on this beam column joint. This picture I have copied from McGregor. It is a simply beam column joint, and it is understandable from this picture that there is a hogging steel, and that hogging steel is, let me get the pointer, filter pen arrow. So we have the other option of highlighter. So there is no highlighter probably. Eraser, ink color, highlighter, highlighter. Okay. Now, if I highlight this bar, so this bar is anchored in the concrete, and then it is made continuous in the beam along the span, and there is a positive steel present in the beam. We can understand that it means this joint, beam column joint, will be subjected to hogging movement, and there will be tension at top and compression at bottom, because the steel anchored within the column is required to get yield at the face of the support at this point, and we know that as per tension control under reinforced cross section we must have tension steel strain greater than or at least equal to 0.005. So this is our uh, tension control under enforced requirement. And compression concrete, on the compression phase, we have the requirement that once concrete crushes at the extreme compression fiber approaching the limit strain, steel at that instant will be either at 0.005 or bigger. It means we are expecting that at the face of the support, this bar will remain gripped and this section will be yielded excessively, and eventually concrete will crush at the bottom. I can also draw the strain diagram for this section at the face of the support. You are well familiar with this strain diagram. So I may say that if it is 0.003 at the face of the support in concrete over here, steel should be greater than or equal to 0.005. So this is our tension controlled under reinforced sectional response. Now question arises that can I hold the steel without slip at and at this section can I get yielding excessive yielding of this steel, because once it is subjected to tensile force, bar will tend to be pulled out from this side and this side. There will be a force applied, and in order to keep it gripped, there must be a friction at the interface, at the contact area between steel and concrete, and there is a chemical adhesion, natural chemical adhesion between steel and concrete, and lugs or deformation on the surface of the bar will also provide bearing component and hence resistance against the slip or pull out. So these three mechanisms, friction, natural chemical adhesion, and deformations on the surface of the bars providing bearing component, are the key factors which develop the bond or resistance against slip. On this side of the section, we have a reasonable length, and I can go straight and I can calculate that up to how much length I can sufficiently grip the bar so that at the face of the support, bar will get yield without slip. However, on this side of the left hand side of the section, which is maximum stressed, I have a limited gross depth of the column. If I still want to go straight, then probably I need to thread the steel, and a nut outside can let the bearing can generate the bearing component and can prevent the slip. Or I may weld a plate on the bar and embed that plate in the core concrete of the column, and then again the bearing of the plate will resist the pull out of the bar. Thirdly, I may have a 90-degree bend or otherwise a 180-degree bend, which can give me sufficient anchorage and resistance against slip and can let the steel yield at the face of the support. So it means in order to let the steel yield, I must have a sufficient development length. So development length means that length which is required to get the steel yield. And I may have this length straight, or I may try to get this length by either using some mechanical anchorage or providing 90-degree bend or 180-degree bends. So in this way, bond and development length becomes so important that the reinforced concrete cross section, which is in equilibrium, and we say T is equal to C, it can be realized and T can be developed and a composite action is ensured. I just want to explain this point little further. For example, we have the idea that below neutral axis there is a C, and above neutral axis, because it is a hogging section, there is a T. And the contribution of concrete is bigger in tension. So above neutral axis, there is no contribution of concrete in resisting bending tensile stresses. And all the tensile stresses are developed by the steel. But it is important to note that above neutral axis, concrete is enveloping the bars. It is responsible to bond the steel with the concrete, and the concrete cover is so important that it is actually developing the composite action. So although above the neutral axis we consider negligible role of the concrete in resisting bending tensile stresses, but its role is important in development of the bond. Otherwise, I can say that the bar is in vacuum. If will be in vacuum, it can't develop composite action. Imagine that you have a cross section. In that cross section, you put a conduit, and in that conduit, you loosely place the steel bar. And then you start expecting that C will be developed by the concrete and T will be developed by the steel. Sadly, you are mistaken, because this T can't be developed until and unless you have a bond between steel and concrete. So either you put the grouts and try to bond the bar with the concrete, remove the conduit, or otherwise use some epoxies to grip the bar with the concrete. It is just like that before concreting, you actually grease the bars with the oil or some greasing, uh, you can say, component. You actually have tried to intensely debond the steel from the concrete. So this is not, you can say, a right approach to debond the bars from the concrete. So friction between the steel and concrete at the contact area, natural chemical adhesion between steel material and concrete paste, and moreover the deformations on the deformed bars are the key components which are developing the bond. Furthermore, in PRC1, we studied that hogging movement at the face of the support when beam is resting on the column. The hogging moment coefficient we learned was, which was negative 1 over 16. When beam is resting on beam, then it is 1 over 24. But when beam is resting on RC column, it is 1 over 16. So for this movement estimation at the face of the support, if all the limitations are fulfilled, ACI moment coefficient can give me M negative at the face of the support equal to 1 over 16 into ultimate UDL into clear span square. So this was our calculation of negative movement at the face of the support. And you use this M negative to calculate area steel, and that internal capacity equation was AS Fy into lever arm along with a capacity reduction factor phi, and it was made equal to the external demand, which is Mu negative. And using this equation, you actually got for your design purpose area of steel. And that area of steel, what you got, you are requiring that this area of steel must yield, it must yield excessively, it approaches 0.005 or bigger strain when finally concrete will crush. So it means all this calculation theoretical bases are that we have a perfect bond between steel and concrete so as to get yielding of the steel. And this I can only achieve if I am well informed that if I am requiring excessive yielding over here, then how much length I must have on either side of the maximum stressed section to let the steel yield. If I go straight or I have a hook or bend. So this is called as development length, which we want to discuss in today's lecture. So now from this simple picture, I have one other point of discussion. Let me rub the lines. Notice that on this picture, the positive steel is going straight into the support without any hook or bend. Up to few millimeters, it is penetrating the core of the column. So it is recommended in ACI code that when you have a beam column joint and this beam is not the part of a lateral load resisting system, it means earthquake combination cyclic loads are not expected. It means tension will remain tension at top and compression will remain compression at bottom. So there is no chance of stress reversal. So it means we are not worried that I need the shielding at the face of the support under stress reversal once cyclic load will attack. It means if I have a push and pull and stress reversal, then there are chances that T will come to bottom and C will come to top. For such cases, you have to also make sure that this steel, which is bottom steel, should also be developed. And you may get in some details, pictures that not only the top steel is anchored, but also the bottom steel is anchored with 90-degree bend. So that is the actually push and pull scenario, and then just penetration of the positive steel inside the support up to few millimeters. Recommended is 150 millimeters, 6 inches, like in this sketch. So this sketch can tell us that actually we are not expecting stress reversal. So just these are hanger bars and these are hanging the ties. So first tie is placed at S by 2, which is the spacing between ties, and then onward the ties are spaced at S. In the column ties are present, and within the beam column joint again ties are present. So in joint we also need confinement and ductility. So these two ties are also present within the beam column joint. And you will study design of joints, then you will also understand that how to calculate these ties within the joints. Column ties, you have designed and studied that how to design the ties in column. And the beam ties, we know that the shear design of beams. So this is a brief discussion on a beam column joint. Now what I tried to discuss on the picture on slide number 4, there is explanation given about the same contents in a reinforced about the same topic. In a reinforced concrete beam, the flexural compressive forces are resisted by concrete, while the flexural tensile forces are provided by reinforcement. So, as I said earlier, C is equal to T. So, both C and E will be present in a reinforced concrete beam. And for this process to exist, there must be a force transfer or bond between two materials. If I say C is equal to T, I can only get this equilibrium if there is a force transfer or bond mechanism present between the two materials. For the bar to be in equilibrium, bond stresses must exist. If these disappear, bar will be pulled out and tension will drop to zero and beam will collapse because section will fail. Now, furthermore, to get idea about these bond stresses which are present at the contact area between steel and concrete, we can take example of this simple beam which is half of the length shown and assume that there is a point load right in the middle. You know that if there is a point load on a simply supported beam, then M is equal to PL by 4. P is the mid-span load, length is L is the length of the beam, and this will be the maximum coordinate at the mid-span. It means we are expecting that once I will design this beam for this maximum mid-span movement, I am calculating that for this M, suppose this is PU and this is my MU, so I am requiring that against this positive movement, I will have an area of steel which will be at sufficiently strain beyond yielding, and the same equation will give me that area of steel which will be at 0.005 or bigger with the lever arm between steel and concrete LA, which is this one. And this is how I actually design. I take 5.2,
ठीक है
right? So in this way, this area of steel which I provided in this beam is based on the condition that T will be equal to C. And this T will be ASFY. And further, the strain in the steel will be 0.005 or bigger when concrete will get 0.003. So strain diagram is also known. I know that it should be 0.005. And concrete over here will crush finally. So again, question will arise that can you get this yielding without slip of the steel within the concrete mass? So it means pull will be applied, and on either side, bar will tend to be pulled out, and from this side also, this maximum stress section, it will tend to be pulled. From On either side of the maximum stress section, there must be resistive stresses. So shown with these arrows that on the contact area between steel and concrete, natural chemical adhesion, friction will be only present if this bar is plain. But if this bar is deformed, then even the bearing on the deformations will also cause the resistance against slip. So in this way, I can say that along this bar, up to certain length, I will have the resistance greater than or equal to T, and then I can see that at this section, the bar will be giving 0.5 or bigger without slip. Please mute your mic. इसका mic खुला है, background में बातें कर. Please mute your mic. So in this way, we can understand that friction, natural chemical adhesion, and if deformations are present, they are holding the bar and not letting it to be slipped. So this is actually the presence of bond stresses on the contact area between steel and concrete, which are causing the resistance against slip. Furthermore, किसी स्टूडेंट का माइक ऑन है, प्लीज ऑफ करें. Now I want to discuss one more aspect on the same picture. Let me rub the lines first. Now the point is that suppose that on this load application, a discrete track appeared over here and other discrete track appeared over here. And we know the movement diagram, movement ordinate is M1 and movement ordinate at the second track, suppose if it is, let it be, this is M1 and this one let it be M2. So the point at which track appeared, applied movement at this section is M1, and where second track appeared, applied movement, which may be ultimate or the service. So at the moment, I am not talking about whether it is the service or ultimate. This is against that P, the movement ordinate. So we can have a change in movement between two tracks, and let the distance between two tracks is L, small l. It means I can say M2 minus M1, and I can use delta M to represent this change in movement between two cracks. Now you are well familiar that what is M2 against this M2 external applied movement, there will be internal resistance, and that will be area steel, which is present in the beam at some stress. I can use subscript Fs2 into lever arm. So this movement will subject the area of steel which is present and reinforcement in the beam to Fs2 stress. Similarly, M1, which is little less as compared to M2, will also subject the reinforcement to a stress magnitude Fs1 with the lever arm La. If I take the difference between them, as I have given on the upper line that M2 minus M1 is delta M, I can say delta M is then equal to, I will take As common outside and I will say As into Fs2 minus Fs1 into lever arm. So you agree with this simple statement difference between the stresses? We are looking at the two cracks which are at a distance L between them. Now it means it will be As and I can say Fs2, sorry, it is Fs2 minus Fs1. Let it be delta Fs into La. So I am using delta, Greek, capital Greek letter delta to represent difference between stresses at two sections which are at distance L. Now, what is actually delta Fs into As? I can also say it is actually delta T into La because As Fs2, I can say it is T2 and As Fs1, I can say it is T1 and T2 minus T1 is actually delta T. So this gives me a very useful equation that delta T is equal to M delta M over lever arm. So now keep this simple derivation in mind and let's move to next slide. Now the same uh, discussion, the slide number 6, they are showing on a free body diagram. Imagine that what I said earlier that there are two cracks and they are at distance L and at section 2 we have a tensile force T2 because Fs2 into area of bar. Let's assume there is only one bar and we are discussing this on one bar. So T2 is equal to Fs2 AB. And at section 1 where movement was M1, we have Fs1 into AB, which is actually T1. And if I want to write that what will be change between two sections in terms of Fs2, I will say Fs1 plus delta Fs will be equal to Fs2. So the same thing either I can discuss in terms of delta Fs or can discuss in terms of delta T. And look at the free body diagram that T2 is greater than T1. So net there will be delta T and against that pull, the resistance is offered by bond stresses, which are present at the contact area between steel and concrete. So we are actually trying to develop a relationship between bar stress, keep in mind change in bar stress, delta F, and average bond stress. Because notice that on the length L, we are showing with equal sized arrows and there is no subscript under the letter mu which is used for bond stress. It means we are actually trying to determine that point by point what are the variations in bond stress along the length L, which is a sufficient length, which is not a very small length, it is a reasonable length between two cracks. So even between two sections which are spaced at length L, variation of the bond along the length, if I can capture, I will call the function or a plot of true bond stress between two sections. But if I have to put just one single value, I will calculate area under the curve drawn for this mu. And once I divide this with L, I can use the term mu average. For design purpose, to make the equation simple, rather than using mu true and determining the variation along the length between two sections, we can replace it, and with sufficient accuracy, we can still get the answer by putting mu average. And now if I will write the equilibrium equation, as I have shown you on the previous slide, that Fs2 is greater than Fs1 because M2 was greater than M1. So delta Fs into area of bar, which is pi dB4 into pi dB square root 4, which is actually stress multiplied by area is delta T. So as a matter of fact, it is T2 minus T1, which is delta T. And which is responsible to resist it is the average bond stress at the contact area between steel and concrete. Since this is stress, and we are saying this at the contact area, so contact area into stress will give me the resisting force against the pull, which is delta T. So what is the contact area circumference into length L? So this simple equilibrium equation is so useful that if I know change in bar stress, I have delta T, I have the average bond stress values with me, I can calculate which length I need to resist that change in force. Or otherwise, if I know the length between two cracks and I have the idea about delta T, I can calculate the average because both are in equilibrium. Delta T is equal to applied action and resistance, both are equal. Resistance offered by the bond between steel and concrete and at the contact area between steel and concrete. Now the same equation I can rewrite it like this, that taking Fs2 minus Fs1 as delta Fs and going back to this sorry, to this basic equation, Fs2 minus Fs1 dB square over 4 and mu average pi dB into L. Now I want to simplify this. I will say pi will cancel with pi, dB will cancel, and this power will change to 1. So it means what I will be left with, Fs2 minus Fs1 is delta Fs into dB over 4 will be equal to mu average into L. So this is shown over here, that mu average is brought to left hand side and delta Fs2 minus delta Fs2 into dB, because this dB is present along with delta Fs over 4, and length I also brought as denominator A. So this gives me a very useful equation that what is mu average? It is equal to change in bar stress, and this change in bar stress is present between two sections which are spaced at length L. And now, furthermore, if I state that this length is very small and I replace this length with x on a very short length, I am trying to investigate what is bond. So it means if I replace this L with dx, then I am allowed to replace this delta L s with dfs, change in bar stress in a very short distance dx. So if now I'm investigating change in bar stress on a very short distance dx, then it means I can drop average and I will say it is mu true. So I can take dfs over dx on one side and I can say that change in bar stress in a very short length is proportional to true bond stress. So it is equal to 4b over db. So this is another useful equation that if you have in hand change in bar stress, rate of change, and then it means you can also get true bond stress rather than average. You can plot true bond stress variation along the bar length. Now keep all this point in mind, and let's now review this simply spotted beam subjected to point load and midspan. I already explained on slide 6, uh, 4, 5, 6, 7, some of the contents. Now again, repeat the same points and look at this picture. Assume a beam reinforced with one single bar A beam shown with dotted line, and there are two sections 1 and 2 spaced at a distance delta x. And furthermore, you can get movement ordinates m2 and m1 as I said earlier. So change in movement is delta m. So according to m2, you will have fs2. fs2 into area of bar will give you t2. fs1 into area of bar will give you t1. Since m2 is greater than m1, so t2 will be greater than t1. So T1 plus delta T will be T2. And then underneath between two sections, you are also looking at the change in shear force. So you know that the shear force diagram for this beam will be like, so there is a constant shear force because there is 1 point load, positive and negative. So it is shown that on this section, which is of length delta x, between two cracks, what are the internal forces? So M, M2, V, and delta X are shown on this hashed area. Now the same equation which we earlier discussed, that I mentioned on the previous slide, that delta T will be equal to delta M over JD or lever arm. Here we are using JD, but actually JD is lever. So McGregor is using this JD, which in allowable stress design, you learned this, which is a lever arm. You can use the letter LA to represent it is actually internal lever arm between T and C. So delta T was equal to delta M over LA. So what was delta T? We derived it from the previous slide that delta T is delta M dB into mu average on the contact area between steel and concrete on a length delta x. Bring that delta x as denominator on the left hand side. So this equation we have developed on the previous slide. So you know it very well. We also know that delta T is equal to delta M over delta J. So this we derived from the simple equation that T equal to C from force equilibrium. And from sigma M we have this M is equal to T into J. So this delta T I can put here. So then it can give me delta M over JD X. This JD I brought as numerator on the right hand side. So putting this in above equation gives me delta M over delta X is equal to pi dB into mu average into lever arm. We also know that dm over dx, change in movement diagram on a distance dx, is equal to v. Dm over dx is equal to v. So I can say that as delta m over delta x is v, so I can put this v here. So I get other very useful equation that mu average is equal to shear force divided by circumference into lever arm. So if you have the shear force diagram and you know the shear, applied shear, you can also get mu average. So we have very useful equations with us, which we can use for our calculation purpose or for deeper understanding of the stress, bond stress variation along the length of the bar or for calculation of the average bond stress. Another simple test which can further help us understanding the behavior of the bond stresses in reinforced concrete. Now look at the simple axially loaded prism which has the reinforced bar at its geometric center, and you are subjecting that prism to axial tension by gripping the steel in the jaws of the machine. Like UTM you can use in test flow lab or in strength of material lab. Axially load this steel which is present as the reinforcement along the length of the prism at its geometric center. So once you will pull the steel bar, now this bar is not rigid. This bar is encapsulated in concrete. Once this bar is pulled, axial tensile strains are developed. There is a perfect bond between steel and concrete. So the strains experienced by the bar will also be experienced by the concrete. Concrete is weak in tension, so discrete cracks will appear along the length of the prism, which are schematically shown. Now, since some portion of the bar is exposed for gripping purpose, so that portion of the bar has no bond because bar is naked. So whatever is shown on the machine as the load, that load divided by the area of the bar will give you Fs, which is shown here. And magnitude is this one. Now furthermore, once you move along and at some distance, there is a discrete crack appeared, bar will get exposed, bond between steel and concrete will drop to zero. So bar is now exposed. It is just like the bar in unconcealed portion of the prism. So that is the reason over here, stress in the bar will jump to the magnitude which was in the initial exposed portion of the steel. So you will notice that between these two portions, where bar is still encapsulated by the concrete, some of the stresses are taken by the concrete. So there is a little drop in bar stress, dip. And this actually is taken by the concrete. So the maximum almost is right in the middle between two cracks or the exposed and in this way we can state that variation in the steel and the variation in the concrete stress on a simple axially loaded prism can be achieved and we can plot it. Suppose if you have instrumented your bar with the strain gauges and you know at every section what are the strains, you can also record the corresponding stresses in the steel. Now, since on the previous slide I mentioned that the true bond stress has the relationship with change in bar stress, and we said this proportional to true bond stress, mu. We are using Greek letter mu. So now, since you have Fs, you can calculate dFs over dx. So in this portion where bar was exposed, there is no change, it is zero. But once you enter, you will get maximum slope, and where dFs over dx is zero, you will get change in sign in the two bond stress, zero stress, and then you are getting change in sign. So you are having plus and minus. And if you want to take average now, it is right in the mid. So average is right in the mid because equal areas are minus and positive in this ideal test, which is axially loaded prism, in which delta T, by the way, is zero. And we call it in and out bond stresses. So if you can get this true bond stress, you get its plot and then mathematically you write a function to define the variation of true bond stresses, and then if you integrate that function, you can get area underneath. And then divide that area with the length, you will get mu average, which can you use for your equations for simplicity. If you want to keep the true bond stresses, then obviously you need to do integration and do this. You need to write the functions which can explain the variation of the bond stress, which can capture the experimental response. And in this way, you can do the exact calculations. Now, little more discussion on another beam, which is subjected to 2-point loads. And now this beam again has a simply supported end conditions, single span, but the only difference is it has a pure bending zone. So middle third, exactly in this picture, they are not actually equally one third areas. So the 2-point loads are little closely spaced, and we have a more span in which movement and shear both are present. But actually, this area, middle area, is free from shear. And we will have a shear force diagram like this, positive and then negative, but there will not be any shear force here, zero in this region. So again, in this region, it means delta T will be equal to zero. It is just like axially loaded because M is constant, delta M is zero. But here we have M1, M2, M3, so delta M will be present, delta T will be present. Now look at the variation in steel stresses. In this portion, variation is just like axially loaded prism. We have jumped stress in steel because bar will get naked and all the stress will be taken by the steel. And once we enter the zone in which shear and movement both are present, we still have a crack we have. At that crack, there is little ease in bar stress because concrete contribution is zero. Bar is exposed, there is no bond, but once it enters the concrete between two cracks, there is little dip drop in the Fs. That is actually taken by the concrete. Similarly, now you have plot of Fs. You can also draw dFs over dx. We learned that it is proportional to 2. So once you plot this, you will get again some in and out pictures, but now positive and negative area is not equal. However, in the middle, like axially load prism, we still have positive and negative area equal because delta T was 0 in that region. And then on the right hand side, we have more positive area and less negative. So mu average, if you want to take, now this mu average will not be through the center, it will be slightly off center. In the middle portion, it will be right in the center. And in this portion, it will be little up from the positive and negative area. So you need to take area under the curve and then divide this with the length to get average. So in and out bond stresses are drawn as true and mu average is shown as well. Now on slide number 11, a very simple test which is very popular to perform. So this is the last slide which I will explain in today's lectures because other sections I have covered the contents up to this slide. So are you there? Can CR please
Yes, sir.
Yes, sir.
Respond. Good. Good.
Yes, sir.
So let me leave this slide, then I can invite questions or we can wind up later on, right? Now, a simple pull pull out test. Very important test and simple to perform in laboratory, and you will see in test flow laboratory some MSc students are performing this test. Has some demerits and some merits as well. I will talk about them. Just take one important aspect that this is a cylinder, and this cylinder has some concrete of certain compressive strength. Once you cast the concrete in the cylinder, along with that, you placed a bar inside of known dia, maybe number 25 or number 19, up to its known embedment length inside the cylinder. You know it that how much length is inside the cylinder. The cylinder may be 6-inch dia by 12-inch height, 150 by 300 millimeter, and you kept 50 millimeter or more below the tail of the bar. So you are not actually providing the bar to its full depth embedded in the concrete. You know the bar grade as well. You know this bar which is present in the concrete cylinder is of grade 420 or grade uh, grade 300. So you have a complete idea about the grade as well as about the dia. In addition, once you will pour the concrete in this cylinder, simultaneously you will pour the companion cylinder or cube. Those companion cylinder or cube, you can crush them at 28 days to determine the FC prime of the concrete in the cylinder. So you know in case of testing that if you are planning that you will perform this pull out test at 28 days, at the same age you will crush the cylinders in the laboratory to correlate that what concrete you have used in the pull out test sample, what is the compressive strength of that concrete. So for this correlation, you have tested the 28 at 28 days your companion cylinders. Even on the bar, you can perform a open test, and the bar where you uh, taken a sample out of it, the same specimen taken out from the same piece of length, you can test in the machine to verify that what is the grade of steel which you have used within the cylinder. So in this way, you have a good information on dia, steel grade, and concrete strength. Now you are putting the cylinder on a plate with the protruded portion of the bar through the hole between the plate, and then you are gripping this exposed portion of the bar in the jaws of the machine, and you are pulling it, and you are recording on the machine on a dial what are the load increments. For example, you started with 0. Obviously, machine was idle, then 1 kilonewton, 2, 3, 10, 20, 30, until needle halts and your load drops. You record that value, and suppose that value is, just for assumption, I am saying it is 50 ton or 500 kilonewton. So that value is the tensile force you applied on the bar, and at that maximum force finally needle halt, and the reason may be bar pulled out, concrete splitting taken place in the cylinder. And the third, which is very rare, that bar may fracture, which is little unbelievable that concrete was so strong that it has held the steel firmly and eventually steel fractured. Yes, it can be true if you have used some very small dia and your bond was so super that it was not letting the steel slip or concrete split it, but steel fracture. So I will discuss this possibility. But at the moment, we have the idea that the load at which the machine shows that now there is no more load increment and your machine stopped, indicating load. Now you record this T, take it as delta T. And you have learned from the previous slides that against this force, what is the resistance offered? Mu average into contact area, which is pi dB into length. You know the length, you know the diaphragm. So it means the only unknown then will be mu average. So it means from this test, you can very easily calculate average bond stress because you know the brand of concrete, strength of concrete, and once you get the mu average, you can propose its relationship with S prime. So this is one aspect of this test. There are some demerits because in this case, you are pulling the steel while the concrete at the interface between plate and the cylinder is having frictional component. Moreover, the bearing on the plate is causing compression over here, compressive stress, bearing compressive stress. This frictional component will not let the concrete dilate. So your Poisson ratio, lateral strain over axial strain, will not be freely allowed. So crack opening and widening will be restricted. While in reality, we learn in all the beams, when bar is in tension, concrete is also in tension. So the environment around the bar is not so conducive as it seems to be in this pull-out test. So this is not a good simulation of reality. So these are its demerits that we have a frictional component and concrete in compression while only steel is being pulled out and steel is in tension. Concrete surrounding the bar is not in tension, but it is in very ideal compression conditions. So this is one big demerit, which is the reason that now in addition to pull-out test, we also perform beam test to simulate the reality. But still, looking at the picture B and C, the same discussion we can carry out that what was the exposed portion of the bar is subjected to Fs. Once bar entered the concrete, there is a little drop in the bar stress, and because concrete was providing the required resistance along with the length, because there was a bond between steel and concrete. So this recording of Fs variation in the bar stress we can carry out if we have instrumented the bar with sensors, and I can record slice by slice the strain and multiplying the strain with the modulus of elasticity, I can get the stress. Similarly, on the third picture, if I have the Fs, we learned that dFs over dx has the proportionality with mu. So similarly, I can calculate true bond stress variation and look at the function. It is a very complex function, so you need to write a mathematical function to capture this curve. Then area under this curve can be calculated. So preferably, if you have not done any instrumentation and simply you know the force at which bar pulled out, you can calculate with reasonable accuracy mu average based on this test. But with the limitations that this mu average calculated is based on a test which has the concrete in compression. Unlike reality, in which we have seen everywhere that bar is in tension, concrete surrounding the bar is also in tension. There is no friction bearing component as it is in the pull out test condition. So I think this is the last slide today's lecture. So I will upload video and let's hope that my voice along with the slides will be available in the recording. Otherwise, you are advised to watch the videos I earlier recorded in section A, B, and C. So CR, please unmute your mic, and if you want to say something, please go ahead.
सर जो रिमेनिंग बाकी है